Okay, good afternoon. We're continuing on the Markowitz model today. Okay, 11. Let's see if we can't get a better pen here. Oh, good. Let's get a better pen. Okay, it should be okay. Okay, on the Markowitz model, we're going to solve it Markowitz mean variance portfolio model. We're going to solve it with the Lagrange multiplier method. And we can see the Lagrange multiplier method can be found in Appendix B of our text in the back. Okay. And first we'll consider the two-asset case. And we'll see how the two-asset case looks, and then we can extend our results to the n-asset case. Here, we have the following, that our x1, x2, our decision variables here are w1 and w2. So it's a proportion of our budget spent on asset 1 and spent on asset 2 in our portfolio. Also, we have n equals 2 decision variables plus we have lambda 1, let's let lambda 1 equal lambda, and lambda 2 equals mu here. This is just a notation that the book uses. So we have m equals 2 constraints. If we have the two-asset case. So in the two-asset case, we get a total of 4 unknowns. Now let's see what equations we have to solve for these unknowns. let's form that Lagrangian. Two asset case. Okay, and that's the following. We'll say L of W lambda mu, and this W, of course, is W1, W2. Okay, so there are two variables there. So we have four variables here. Equals 1/2, and this 1/2 is just to make our life a little simple with the algebra. W1 squared sigma 1 squared plus W2 squared sigma 2 squared plus 2W1 W2 sigma 1 2. Okay. Minus, now in the objective function, we multiply the constraints by the Lagrange multipliers and subtract them off. Minus lambda times, in the first constraint, R bar 1, W1 plus R bar 2, W2 minus R bar. And what is this? This is just G1 X minus B1. And we also have minus mu, the second Lagrange multiplier, times the second constraint, W1 plus W2 minus 1. And here we have our G2X, if you like, where X is W, and this is minus B2. The 1 is B2. Okay. So now we need to, let's evaluate our, first, let's evaluate our necessary conditions. Remember, our necessary conditions are what? Our necessary conditions are that, in general, it said that the partial of the Lagrangian with respect to the first decision variable equals ... equals the partial of the Lagrangian with respect to the nth decision variable. In this case, we have n equal 2, equals the partial of the Lagrangian with respect to the first Lagrange multiplier, that's 1, equals ... equals the partial of the Lagrangian with respect to the mth Lagrange multiplier, equals 0. This was our equation star. So our necessary conditions for an optimal. This is just a an n plus m dimensional extension of our ordinary conditions where we set the first derivative equal to 0. Now we have the partials here. For us, we have at x1, x2 equal w1, w2 So n equals 2. And we have that lambda 1 equals lambda, and lambda 2 equals mu in our case, for our m equals 2. Okay. So let's look at these here. Let's start evaluating these partial derivatives. So first, let's take the partial derivative of the Lagrangian with respect to W1. Okay, and here we're going to get the following: 1/2 times 2W1 sigma 1 squared, okay, plus 2W2 sigma 1, 2. The second term has no W1 in it, so that doesn't matter. Minus lambda r bar 1 minus mu equals 0. Okay. Now, we can, here's where our 1/2 comes to play. We take this 1/2 and multiply it, so we can cancel out there. So that's all the 1/2 helps us with. Or we can express this the following way. We can say that W1 sigma 1 squared plus W2 sigma 1, 2 minus lambda r bar 1 minus mu equals 0. Okay. And this equals, let's write this as the sum of the Wj sigma 1j over j equals 1 to 2, okay, because if j equals 1, then we just get the sigma 1 squared, the variance. If j equals 2, we get that covariance term here, okay, minus what? Minus lambda r1, r bar 1, minus mu equals 0. So this is our general term there. So we have this. This is our partial of the Lagrangian with respect to W1. Now, let's take that partial of that Lagrangian with respect to W2. And bear with me for this. This is a lot of algebraic gymnastics, but let's just take care of it. So we want the partial of the Lagrangian with respect to W2, the proportion of our budget invested in asset 2. And that equals, again, we have this 1/2 out here. That's going to simplify things. Now we have 2W2 sigma 2 squared. W2 sigma 2 squared. Remember, we don't have the sigma 1 squared because we only have a W1 term in front of that, plus 2W1 sigma 1, 2. Okay. And of course, sigma 1, 2, or we can say that this equals sigma 2, 1. In fact, that's what it is, sigma 2, 1 first, minus lambda r2, r bar 2, minus mu equals 0. Okay, there's our term here. Or, expressing it like we expressed the last one, we could say, let's look at the sum. J equals 1 to 2. because we have two decision variables, W1, W2, Wj, sigma 2j, okay, because when j equals 2, we get the variance. J equals 1, we get the covariance here. Minus lambda r bar 2 minus mu equals 0. Okay. So this is our second partial. Okay. So that the partial derivatives of a Lagrangian with respect to Wi are of the form, we just extend this for n variables, or n assets. Here we have the following. We have the sum j equals 1 to n. Okay, Wj sigma ij minus lambda times r bar I minus mu equals 0. And this is for I equals 1 to n. So we have n equations here. This is equation 6.5a, page 159 of our text. Okay. So this is a system of n equations. Here. And we also have, what else do we have? Have the two equations from our two constraints. And these are the following. We have that the partial of the Lagrangian with respect to lambda equals the partial of the Lagrangian with respect to mu equals 0. So these are our star kind of equations. And these are, in fact, easy. And let's look at them for n variables. Let's say W1 through Wn, we have the following. The sum of the Wi r bar I equals 1 to n, equals r bar. Okay, and this is equation 6.5b on that same page, page 159. And finally, we have the following. We have that dl du d mu equals 0 implies that W1 equals W2, or plus W2, excuse me, equals 1. This is our second constraint. In fact, when you take the partial derivatives of the Lagrangian with respect to the Lagrange multipliers, you always get the constraints back here. Okay. Or, in general, for n assets, if we extend this to n assets, we get the following. We get the sum of the Wi, I equals 1 through n. Okay. Here we just had the n equals 2 equals 1. Should be a 1 here. And this is equation 65C. Again, on page 159. Okay. We should have put this in blue, highlighted that. Let's highlight this. So what do we have? So for n assets, for the n asset case, we get n plus 2 equations we should say the n asset and m constraint, 2 constraint. Let's write this out. M equals 2 constrained case. We get n plus 2 equations and n plus 2 unknowns. If we had a general m, we would get n plus m equations and n plus m unknowns. So we can solve for this with no problem here. Let's put this away. Good. Okay. So that's how Uhlenberger derives these equations for the Lagrange multiplier approach to the portfolio selection problem for the Markowitz models. Now, notice also for our portfolio problem, selection problem, we have an objective function of the form f of x equals x squared, right? Because what are we doing? We're trying to minimize the variance. So all those variance terms, they're either, for the strict variances, they're squared, and for the covariance, they're one thing times another thing. So it turns out to be squared. So this is convex because if you take the first derivative of a function of the function x squared, you get 2x, and the second derivative equals 2, which is greater than 0 for all x. Okay. So why is that nice? Why is this the case? If we draw this, let's see if we have our little blue pen here. Yes. If we draw this, we get something like the following. Call this f of x. You can't see that very well. Let's do this, f of x. And let's call this guy x. So in a convex function, we look something like this. And what's happening here is that if you take the first derivative you can set that equal to the tangent. The tangent is to the curve is at any point is equal to the first derivative of the function at that point. And what do we have? That first derivative equals tangent is increasing. It's increasing. That first derivative is increasing implies that the second derivative must be, in this case, it's strictly greater than 0. In general, all we need is for greater than or equal to 0. In general. Okay. So the way to test if this function is convex, if you have a differential function, you just take the second derivative and check that it's greater than or equal to 0 for all x. So what? So who cares? Who cares? This, of course, we care because we could say who or why care. We could say that, so the portfolio selection problem satisfies the sufficient conditions of our Lagrange multiplier method. So, and that implies an optimal solution to, and let's call that W1 to Wn, and we'll say lambda and mu. Optimal solution to the Lagrangian problem and let's call this W, these are stars, let's put these stars here, yields an optimal solution W1 star up to Wn star for our original problem. Okay. We also have to note also that the two constraints are linear equality constraints. So if we have linear constraints and we have and we're minimizing and we have a convex objective function, then the Lagrange multiplier method is guaranteed to give us an optimal solution. All we do then is just solve for the necessary conditions. Okay. This kind of puts to rest our portfolio chapter, which is a long chapter, and it's very important. Okay. Now, let's go on to a new subject. And we'll call it the capital asset pricing model. Yeah. CAPM. And so typically we call this the CAPM model here. What is the CAPM model? Okay. It's an equilibrium model that was developed by William F. Sharp You can see his name Sharp in our textbook when they talk about the Sharp method for evaluating whether a portfolio is efficient or not. And Sharp shared with Markowitz the 1990 Nobel Prize in economics. So what is it? CAPM is trying to find At equilibrium, what should be the price of our various assets here? It also has significant computational advantages over our mean variance approach. Markowitz approach. We'll see this, we'll do an example, and we'll see this in a second. Okay, but first let's talk a little bit about this CAPM. CAPM is a very important model. Not everybody believes it, but it's very important in portfolio theory. Now, so the CAPM answers the question, at what should the equilibrium price of an asset or stock be? And it answers this in terms of the total market and we'll call the total market M price. So we'll see how each asset moves in relation to how the market moves. Today the market moves a lot. It was down heavily in the beginning, and then it came back up, and it was just about even the last time I looked at it. So we have a lot of volatility lately. Okay. Now, first let's do the following. Let's look at assumptions of the CAPM. And if you look at different texts, you'll see that different texts give different set of assumptions. We'll consider these assumptions. One, it says that individual investors cannot affect prices, asset prices, by their trades. In other words, the market is made up of a number of small investors. A market comprises a large number of small investors. Now, of course, this is not, we're making this assumption, but this is not the case here. The market is made up of small and large investors. There's some large hedge funds and mutual funds in there. And sometimes what some investors do can actually make the market move. 2, we'll say that all investors plan for one holding period. Why don't we say only one holding period? So we're talking about short term here. What are some of the other assumptions? These assumptions are going to lead us to some neat results. Three, we'll say that investors form portfolios from the set of all assets or stocks, if you can think of this, plus they have access to unlimited borrowing or lending at a fixed risk-free rate. So if investors see something that they think is a great investment, they can actually borrow money at a risk-free rate and use that money to invest in that asset. This is not necessarily a realistic assumption, because not all investors can borrow at a fixed rate. No taxes or transaction costs are paid by the investors. So obviously this is a simplifying assumption, because obviously investors have to pay taxes, and when you make a trade you have to pay a transaction cost. Now, this is not necessarily true, and you don't have to pay transaction costs. Typically, if you have a retirement account and you change the percentage that you want to put in, say, a growth or stock or equity index or international funds or money market or bonds, typically you do that with mutual funds, switching around your portfolio, your retirement portfolio, and you don't pay any transaction costs. Now, most retirement accounts, instead of charging you transaction costs, limit how many times you can go in and out of an asset in terms of timing. Because otherwise, that you'd be a free rider, that other people who own that mutual fund would actually be paying the transaction cost, because obviously the mutual fund must incur transaction costs. Okay, our fifth assumption is that all investors are rational, mean variance, optimizers. That is, they all seek to construct efficient portfolios. Okay. One more. Oh, here's the last one I'll give. 6. All investors analyze assets, in other words, stocks, in the same manner and they all have access to unlimited data. In other words, they all have all the data that they need to construct this. Now, we have these 6 assumptions. Some books have less, some books have more. Let's see, what are the implications of these assumptions? So this is important. First one says that all investors will hold the market portfolio. And we'll call that M. Okay. Okay, why? Why is this? Okay. By assumption, all investors will hold the same portfolio. They're all mean variance optimizers. They all analyze assets in the same way, and they all have access to unlimited data. So they'll all hold the same portfolio. There's no reason why any one of them would hold a different portfolio. Therefore, if they all hold the same portfolio, it must be true that, therefore, that portfolio must be the market portfolio. In other words, in their portfolio, they'll have each and every asset of in the market, M. Else, what would happen? There would exist assets that are not held by any investor. Okay. So they all have to hold this market portfolio. They all hold the same portfolio, and they must own the market portfolio. Otherwise, we would have assets that nobody would be purchasing or hold, which is impossible. Okay. So a second assumption is the following. 2, the market portfolio M will be efficient. It's on the efficient frontier. Okay. Now, the key thing here is the following. Here's another key implication of this. And this we'll go over again next time. Number 3, let's put 2 stars here. The risk premium in other words, the reward for bearing risk of any asset I is proportional to the risk premium of the market portfolio. And the way it's proportional, we'll see next time, is by something called a, we'll call beta I here. Okay, so that's why you hear about people purchasing betas. If you know how an asset will move relative to the market, you know a lot. Okay, I think that's enough for today. I think we're almost out of time, in fact. Thank you very much. We'll see you tomorrow. Hope it's a nice day where you are. It's a nice day here. And is the third game on tonight?
Yeah, I think so.
Okay, so do your homework before or after the third game, okay? We'll see. It's a 1-to-1. We'll see how they do.